So let me now start how to understand these estimates beta naught and beta 1, how good they are, how accurate they are. So let's just go back to this line that I recalled before I finished the previous lecture. So on the first day, we did these several lines, right? We just took 100 lines and said, okay, which is the best line? So that's one way of doing it. You draw many lines and you try to find the best line from the lines you've drawn. But here I have an estimate for beta naught or beta 1 hat from a particular method. So in this lecture, I'll try to explore and give you an answer for that estimate. Okay. So for this, I am going back to a very basic statistics idea from which you may have seen in probability. So I'll just do it again, just to sort of. So I'll use the same notation as what we're going to do, so that it's not conventionally used. People use X for the mean, but X for the data population, but I'll use Y. So Y is some characteristic population. Let's say the height of people in the population, or the age of a population, and so on and so forth, or the mean, or the income distribution in the population. Some characteristic that you have in mind. So now I want to understand how the mean of the population looks like, or how Y looks like. So one thing people do is people first understand the mean of Yi and the variance of Y sigma squared. And let's say you want to estimate this mean. So what will be given? So what we'll do is we'll go to the population, we will sample, and then we will get some data points. Let's call them Y1 through Yn. Right? So from this, I'd like to estimate the mean mu. So let's write down, that's the goal. So let's try to estimate the mean mu from the data. So how does one do this? So you have data points Y1, Y through Yn. That's all you have about the population, right? You don't have anything else. And you want to estimate what the mean of the population looks like. So what would you do? You would first go and say, okay, fine, this is all I got. So I'll take the empirical mean and I'll think of it as an estimate of mu. Right? This is what you've done in your statistics 101 class. Right? Now, again, the key question then is this a little different question? Is this mu an accurate estimate? Is this mu hat an accurate estimate of mu? Right? This is something that one can naturally ask. So how does one answer this question? So if you have seen in your statistics class, let's just do an extra calculation maybe, and come back and do this. So let's see, let me add this here. So let me come back here. So we'll write this down. So this you're done in, it's an aside calculation. Let's say an aside calculation from earlier. Right. So here you've done it in your calculus statistics class that, okay, so you have mu hat is equal to 1 over n summation I equal to 1 to n of the yi's. Then you know that the expected mu hat depends on the sample that you've got. And note that y1, y2, yn is a random sample, right? y1, y2, yn is a random sample. Right. So E of mu hat is going to be 1 over n, the sum from I equal to 1 to n, E of yi. So here what did I use? I used the fact that the expectation is linear. Right? That's all I used here, right? So I used linearity of expectation, right? So I used linearity of expectations. And now this just is a simple algebra. Each of this is mu, so it's 1 over n times mu, and you get is just mu. The n cancels off, and I get mu. So the mu hat is an unbiased estimate of mu, right? So that's one thing you immediately know. Mu hat is an unbiased estimate of mu. Okay, so let's go back to our calculation. So we have already observed that. So let's write this down. So mu hat is an unbiased estimate of mu. So sorry about that. So you should always keep in the background of your head. Can I carry this over to beta naught and beta 1? Right. So the answer is true. We will do that. We will do that as well. So this is a question that we will verify. So once you have an unbiased estimate of mu, how do you judge its quality, right? So I have the estimate mu. So mu is somewhere here. So let's say mu is somewhere here on the mu hat is somewhere here on the real line. So how do you judge it's random because mu hat is coming from the sample, which is once. How do you judge its value? You know it's going to be centered at mu, right? That's how mu hat is, right? Right? And then what you do is if your estimator, so this is the estimator, this is the mean of mu hat, right? You say an estimator is good if it has small variance. That is, if the variance of mu hat is small, right? So then you could potentially say that mu minus sum, let's say 3 sigma to mu plus 3 sigma is kind of the effective range of mu, right? Range of mu hat, right? So this is one way of assessing the model. So if you compute the variance of mu hat, you're in business. Let's just go check. So how does one do that? So if you go and check, so I'll do the first few steps, and you can go and check it yourself. That if I have, so let's say, so if mu hat is equal to, I have 1 over n, the sum from I equal to 1 to n of yi. So let's see what's the variance of mu hat. The variance of mu hat, if I do a calculation, is going to be 1 over n squared times the variance of the sum. Now I'll leave it as a simple exercise to check. So I'll just leave this as an exercise for you to check that. So what is true? What property of yi can I use to write this as 1 over n squared times the sum from I equal to 1 to n of the variance of yi's. Okay. Once I do this, then I'm in business because this is just 1 over n squared times sigma squared times n, and there's sigma squared over n. So that's the variance of mu. So I can think of this here, the true mean is mu, and the true variance, so this is sigma squared by n. So now you can immediately see how good the estimate is, right? Because as n gets larger and larger, this interval is going to get smaller and smaller. Right? So it means for the larger sample size, the variance is going to get smaller. So this is called variance reduction, which I'll summarize next. So let me just copy this down properly so you can see. I'll write it down neatly. So this, and here I use a property of the data set to show that the variance of the sum is sum of the variances, and this simple algebra gives you that. It's 1 over sigma squared. Right. So let's go back to our main calculation. So here, like I said, I'll go back and I get this, right? So this, I've summarized this whole thing. So I've said that is sigma squared by n, and n large means I have a reduction in the variance of mu hat. That means I have a very, very good estimator for large n. So then the key question then becomes, can I carry this over to beta naught and beta 1? Is this possible? And the answer is kind of yes. Let's see how to do that. So again, you go back to how you estimate a beta naught and beta hat given the population. So you have a population, yi and xi. Remember, xi is given, it's a fixed numbers, and you're predicting yi using the model. And given the data set xi, I think of my yi as random numbers with mean beta naught plus beta 1 xi, right? So let's just write this down so we are on the same page. So this is where we are, right? So let's just do this. Let's let's make this white, and let's do a little bit of calculation for ourselves so you understand where we are. So here we go and check. So the first thing we know is that these are all given to us. Let's mark all the given as orange so we know, or yellow perhaps, and all the given ones. So this xi minus x bar is the data set that's got a fixed. So we just take this as fixed, and this one is right. And then given the xi's, I know my, so maybe I'll call it as yellow deterministic. So let me call this yellow, or all deterministic, right? And I know I'm going to assume that the mean of the yi is beta naught plus beta 1 xi, right? And the variance of yi, I'm going to assume, is known as sigma squared, right? That's the model I'm assuming. Okay, that's where I'm from. So now, given this, can I give an interval for beta naught and beta 1 hat? That's the idea, right? So one simple idea is that one simple calculation is that if you just look at the mean of beta naught hat, right, from this simple exercise, one can simply check, right? So the mean of beta naught hat, like before, right, will be equal to, so if you go look here, it's the mean of this guy, which is just beta naught plus beta 1 x. You can just rewrite it as, you can just check, will be truly as beta naught. It's a simple exercise you can check. So I will not go and check it. It just gives you exactly what you want, right? Because I have a beta 1 x coming from this, I have an x bar right here, it cancels off and gives you this thing, right? So beta naught hat is an unbiased estimator of beta 1. So let's write this down and let's forget the side calculation. We'll come back to that later on. So I already shown you that beta naught hat is an unbiased estimator of beta naught. So let's write this down. Let's move this a little bit down so I can sort of, and maybe I'll move this page across so that we don't have to sort of keep on. I'll move the side calculation to the last page of this notes. Then come back and close it. And let's come back here. So I have this line, right? So now from this line, I have that beta naught hat is an unbiased estimator of beta 1. Or beta naught, sorry. Right. So now again, if I do the variance again, so if you look at the variance of this, so this is all deterministic, guys. But of course, beta 1 hat depends on the y, so you compute the variance of beta 1 hat. But the variance of y bar is sigma squared by n. So this is a simple exercise that I'll let you do. I encourage you to do this whole thing, that you do this two-step calculation. That is, one is you check what the variance of beta naught hat is and what the variance of beta 1 hat is. Okay? Again, all you assume is y's are uncorrelated random variables with these ideas, right? So with these problems. Mean is beta naught plus beta 1 xi and variance of y is sigma squared. This is true for 1 less than equal to I less than equal to n. Very good. So once you do this, you sort of have several observations to make here. So given this variance, so let's stare at it a little bit. So now, see, if the xi's are all close by, right, then this is going to be small, right? Then it will have a certain effect on the variance of beta 1 hat. So you sort of cannot predict beta 1 hat very, very well. So they have to be a little bit far away, because otherwise you'll have to, if this is very, very small, you'll have a large variance of beta 1 hat. Similarly, here again, if you look at this expression right here, if you look at x bar squared divided by this, you have to sort of understand that the more the xi's are spread out, you have an clear effect on the variance of beta 1 hat, and similarly you may have an effect on the variance of beta naught hat as well. So let's mark this observation. So the first observation we make is that how good the estimates are is that the more spread out the xi's are, the better the estimate for beta 1 hat is. Okay, that's one thing. So the variance of beta hat is small, and from our aside calculation, we know that this is quite good. Very nice. So now you can do the same thing like you did for the mean, right? So you can do a confidence interval for the right. So let's do this. Let's go back here. Let's do this first. So you remember we can do this in this. Let's do simple exercise here. So this we knew from before, that we had mu minus let's say z alpha sigma squared sigma by root n, and mu plus, so mu hat plus z alpha sigma by root n gave us a confidence interval for mu, right? The alpha confidence interval for mu. So I would just put I just call it a z.95, so we know that 0.975. If we take, and this is a 95% constant interval for mu. This we've done in basic statistics class, right? How to find the interval for mu. Similarly, what I can do is I'll just do a simple, I'll just put instead of 1.96, I'll just put a 2, and then you can do the same thing. You can just get an, because if I assume beta is a normal, then I get the fact that, sorry, I'll make it white. Then this is a perfectly accurate statement I'm making, that the interval estimate for beta naught and beta 1 is just going to be beta 1 hat minus 2 times square root of variance beta 1 hat, and similarly here, and then I do the same thing here. So these are two intervals for beta 1 and beta 1 hat. So this is one way of providing some error bounds on your model. So you have a model and you have two bands. So beta naught hat plus twice the variance of beta naught, square root of variance of beta naught hat is one band, and the other one is the negative side. So that's how your model can spread, right? So the other thing we can do is we can also go and test like we did in the basic statistics class, right? So the other thing is that suppose I have in the basic statistics class, you can devise many tests for the following thing, right? Suppose you had, let's say, mu is equal to 0 versus mu not equal to 0. We devise several statistics tests to see if you have evidence to reject the null hypothesis. So the question again I want to ask is, can I do the same thing for beta naught and beta 1 hat? So I have an estimator. If I have a hypothesis, can I go and test? Can I go and tell you whether beta 1 hat is genuinely not 0? It means that there's a real slope for the line, or just yi is independent. So what I want to do is I want to test if beta naught hat, beta 1 is 0 versus beta 1 is not equal to 0. And what am I doing? The model is, if beta 1 is 0, then the model becomes yi is equal to beta naught plus x1. That means x has nothing to do with y's, right? That's what it's saying. That's what I'm testing here. So let me write this down. So this is the meaning of this is that, so the consequence of this is that, so this is the consequence of h naught, right? So let me write this down. So it's the consequence of h naught. So under h naught, you think that x has no effect on y's. So your whole model is meaningless. So that means beta 1 is 0 when you try this, right? So the other thing that you should keep in mind is that that the standard error for beta 1 hat. So that let's see what is evidence. So one evidence is the following. So let's go check when will beta 1 be 0, right? Or beta 1 be not 0, right? So sometimes if you look at the standard error for beta 1 hat, it's very, very small. But even small values of beta 1 hat is evidence that beta 1 hat is not equal to 0. That means you have a good estimator and you think beta 1 hat is there. The other extreme is that when standard error of beta 1 hat is very, very large. So in this case, large values of beta 1 hat, will that give you, so only large values of beta 1 hat should tell you that beta 1 is not equal to 0. There are two ways of intuitively checking when beta 1 is not equal to 0. So, but in practice, what does one do? In practice, one does a t-test. So this is something that we will check next time. That so in practice, one does a t-test. So what one does is that one checks, if you want to check if beta 1 is equal to 0 or not 0, you look at the statistic beta 1 hat minus 0 divided by square root of variance of beta 1 hat. You show that under h naught, this statistic follows the Tn minus 1 distribution, and you use that to understand with this evidence in the data set to reject the null hypothesis. So we will carry this out next time.